Welcome back. We have proved that if a degree 5 polynomial has Galois group S5 or A5, then it is not solvable. We are yet to produce examples of such polynomials, but before we do that, I am going to reprove this statement, because as promised I am going to give you two different proofs of that statement. So let me prove the following. So this is a result that we already know, but it's a different proof. So let's take a degree 5 polynomial. Okay, so suppose the Galois group of f is S5 or A5, then f is not solvable. Remember, we did prove this because the Galois group f is solvable if and only if Galois group is solvable, and the Galois group is by hypothesis either S5 or A5, so it's not solvable by group theoretic arguments, so f itself is not solvable. But here I don't want to introduce solvable groups. This is a self-contained proof that will work only using that A5 is simple. So basically that is the only thing we need. Okay, so let's start the proof. So suppose G is S5. So let G be the Galois group. First, suppose G is S5. So I am going to argue that I can assume G is A5, and then that will also solve the case for S5. Okay, so then let K be the splitting field of F over K over F. So the G is the Galois group of K over F, right, by definition. So you have K and you have F to begin with. So this is S5, the Galois group is S5. But now first add, let D be the discriminant of F and delta is the square root of the discriminant. Since Galois of F is not contained in A5, we know that delta is not in K. Sorry, delta is not in F. This is something we have shown. Discriminant is a square if and only if the Galois group is contained in the alternating group. So this is in fact a degree 2 extension. It's either a degree 2 extension or a degree 1 extension. But if it's a degree 1 extension, delta will be in F, so that's not possible. So this is degree 2 and Galois, of course, and this is the Galois group A5. That is the only group, if you think about this, of order 2, index 2. So this must be okay. So this implies the Galois group, only group of index 2 in S5 is A5. So this must be a group of index 2, right, because this is 2, so that is A5. So Galois group of F over F delta is A5. Okay, so suppose that we have shown that Galois group, if the Galois group is A5, then the polynomial is not solvable, then F is not solvable over F delta. Okay, so this implies F is not solvable right, because if the roots cannot be expressed as radicals with coefficients in F delta, they can't be expressed as using radicals in F. So if it's not solvable over a bigger field, it is not solvable over a smaller field. Okay, so this is what I will show. This will follow Okay, so if we prove the A5 case, that means forget S5 for the moment. Okay, so if we showed that if Galois group is A5, then F is not solvable, then applying that theorem, Galois group of small f over F delta is A5, so it is not soluble over F5. It will follow in turn that it's not soluble over F. Okay, so it suffices to consider the case Galois small f is A5, because if I prove that case, this implication will follow. Okay, so now we are in business, so we assume, so let G be the Galois group of F which is A5. Okay, so suppose, so now I am done with this discriminant business. So now I have my situation is K over F, this is A5 and it is supposed to be not solvable. So K is a splitting field of small f over capital F. Okay, so if, so our goal, F is not solvable over capital F. Okay, suppose not, or suppose it is. Suppose it is solvable over capital F. That means let alpha be a root of small f in capital K. So alpha is, so this is going to be our assumption and we hope to get a contradiction. Suppose its roots are solvable. So I will take one root. Alpha is solvable over F. So there exists a tower of extensions which are cyclic of prime degree, like this. So what I want to do is F, which is F0 contained in F1, contained in Fr, and alpha is in Fr, and each is cyclic of prime degree, and Fi colon Fi minus 1. Okay, so I need to say Fi over Fi minus 1 is Galois, and the index of this or the degree of this extension is prime. Okay, so now radical is equivalent to, being radical is equivalent to existence of such a tower with abelian extensions or cyclic extensions, or refining further, cyclic of prime degree. So I added this additional condition to you, to the theorem that we did. So I will just show it to you. Remember, we originally wrote 1, 2, 3, but then later I added a fourth condition because it is going to come up later, and it comes up now. So there exists a tower like this where each extension is cyclic of prime order. So it's Galois, and its Galois group is a prime is a cyclic group of prime order, and it's a triviality to go from 3 to 4, because once you have a cyclic extension, you can take a subgroup which is of prime index, go modulo that, and so on. So 3 to 4 is a triviality. So I just added that after we proved this theorem. Okay, and we are going to just now use 4 directly. So we have such a situation. Okay, so now what I will do is the following. So now I have a small claim which is actually the main ingredient in the proof. So let me prove that as a lemma. Let f prime over f be a Galois extension such that the degree of this extension is a prime number, let K prime be the splitting field of small f over capital F, F prime. K prime is the splitting field of small f over F prime. Then I claim Galois group of K prime over F prime is also isomorphic to A phi. So that is the lemma, and this lemma is all that we require. So the main ingredient is the lemma. So let's carefully prove this. So the picture is the following. So you have, I'll draw this picture a few times. So you have F to F prime. So right here, F to F prime, and we have also K. Remember, K is the splitting field of small f over capital F, and we have K prime, which is the splitting field of F over capital F prime. Okay. So now let's just see what these are. So first of all, K is equal to F adjoint alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. Okay. So as a small exercise, I did not say that F is an irreducible polynomial in theorem, but if Galois group of F is A5 or S5, then F is irreducible. This is an exercise for you, because if it's not irreducible, then it factors as GH, where degree of G and degree of H are less than or equal to 4. So the Galois group cannot be S5 or A5. So because K will be, so basically what we know is that Galois group of K over F is, the order of that is divisible by 5, right? Because it's either 60 or 120. In either case, 5 divides this. But if F is reducible, then 5 cannot divide. Okay, so I'll leave that as an exercise. Maybe I'll do this in the exercise session later on. So F is irreducible in order for it to have the right Galois group, A5 or S5. Because if it's degree 4, if it's a product of smaller degree polynomials, it can be, when you attach roots of G, you will have L, this degree is less than or equal to 24. And then you will have another, so this is the splitting field of G, which is degree 4, and then you will have splitting field of H. So that's also less than or equal to 24. In fact, if it's degree, I mean, it will be much less than that, but I don't care. But the total can't be, 5 can't divide the total, okay, product. So anyway, this is triviality, but I wanted to record that, and I wanted to state a stronger theorem, so stronger looking theorem, so I don't want to assume F is irreducible. So basically, let me record it here. F must be irreducible with this hypothesis. So the conclusion that F must be irreducible says that alpha 1, alpha 2 are 5 distinct elements, right? So that is something that I note. And what is F prime? So this is what we have. F Galois group, let's say this is P, okay? So prime, say P, some prime number P, is isomorphic to Z mod PZ. So it is the splitting field of some polynomial, and we know that has no proper intermediate fields, right? It has no proper intermediate fields because it is a prime number. If you have an intermediate field here, that must either be equal to F or F prime, because P cannot be factored as product of two smaller numbers. This we also know that F prime is the splitting field of a polynomial okay, we claim that G must be irreducible. And the reason is similar to above. So it is the splitting field of a polynomial because f prime is Galois. Any Galois extension is splitting field of a polynomial. In this case, separable is automatically there. So I'll just not mention that. Okay, because if G is some h times h prime with both h and h prime being positive degree polynomials, then we have f prime which is f adjoint roots of G, and you can have an intermediate field here, f adjoint roots of h and f. Okay, so this, if this is a proper decomposition, I can also assume that because if they are not degree 1, if any of them is degree 1, I can just drop it and take that as G. If G is h times x minus a, then a is in f. So f prime will be splitting field of h. F prime is a priori splitting field of G, but I don't get anything extra by attaching another linear factor. So I can remove all the linear factors that G may contain. Then if it is not irreducible, it will factor as irreducible polynomials of degree greater than 1. So at least 2. So this is not an equality and this is not an equality because h prime cannot be contained, roots of h prime can't be here, okay? Because they are co-prime, that means they have no common roots. H and h prime are co-prime because they are two irreducible, I mean they can further factor, but I assume that, so their GCD is 1. Okay, so I understand that this is all a bit of work. I mean, this is not such a triviality as I am trying to suggest, but this is an exercise. So take this as an exercise and show that G is a irreducible polynomial. So because you can conclude that these two must be unequal. Okay. So now what we have is G is an irreducible polynomial. So G is irreducible of degree P. Of course, it has to be P because you take any root, its irreducible polynomial is G and the degree of the extension is P. So this tells me that f prime is f adjoined some beta 1 through beta P, right? So it has roots so it splits completely in f prime. So the roots are beta 1 through beta P. So now I am going to rewrite our picture. So K is equal to f alpha 1 through alpha 5 and f prime is f beta 1 through beta P. Now let's take K to be, let K prime to be f adjoined all of them. So K prime is the composite. So this is a composite of f prime and K. Obviously, right? That is the smallest field, let's say in f bar. I need to talk, composites are really make them meaningful only in a bigger field. I can take it to be in f bar, right? Because that is any field that contains both K and f prime must contain alpha 1 through alpha 5, beta 1 through beta P. And this is the smallest such field. And now note that in fact K prime I have used earlier and it is not an accident that, so I should not really talk about new K prime is not being defined for the first time, but I will simply note that alpha 1 through alpha 5, beta 1 through beta p is indeed the splitting field of f over f prime, right? Because this field K prime is generated over f prime by the roots, right? So K prime is f prime adjoint alpha 1 through alpha 5. So f splits completely in K prime and it is generated over the roots, over f prime by the roots. So that is the splitting field of small f over f prime. So now this is our picture. So K prime K prime K f f prime, and this I am going to write now, instead of the degree I am going to write the Galois groups here. Let's call this Galois group G, let's call this Galois group G prime, let's call this H, and let's call this H prime. And what is our claim? Our claim is that Galois group of K prime over f prime is A5. So claim is H is isomorphic to A5. So this is what we want to prove. Right? And I am just introducing a new H prime here, that's a Galois group of this. Everything here is, every extension here is Galois. Of course, because K is Galois, because that's splitting field, F is Galois over F prime is Galois over F by hypothesis, and K prime is the splitting field of actually of Fg over capital F, right? Because the roots of Fg are alpha 1 through alpha 5 and beta 1 through beta p. Or more directly, this is Galois and this is Galois, so the composite is Galois, right? That's all I am saying. So now let N be the Galois group of K prime over F. Let N be the Galois group of K prime over F. Okay, so now I am going to just do some serious group theory. So what do I do? And we have, so then let's list down all the statements. So H and H prime are normal subgroups because these extensions are Galois, and G or N mod H is isomorphic to G prime and N mod H prime is isomorphic to G. This is from main theorem of Galois theory. So far so good, right? So there is nothing serious yet. This is N, modulo H is G prime, this N modulo H prime is G. Okay, so now consider the first, we claim that H intersection H prime is identity. So the proof is simple here. Suppose sigma is in H. What does this mean? Sigma is in H means, what is H? H is the Galois group of K prime over K. So these are automorphisms of K prime that fix K, which is generated by alpha 1 through alpha 5. So sigma is in H means sigma fixes alpha 1 through alpha 5. Sigma in H prime means H prime is the Galois group of K prime over F. So these are automorphisms of K prime that fix everything in F prime. H is the Galois H prime. Okay, sorry. Let me write H prime here. Let me write H here. H prime is the Galois group of K prime over K. So automorphisms that consists of automorphisms of K prime that fix K, and in particular that fix alpha 1 through alpha 5. So let me say F automorphisms of, because F is fixed and then alpha 1 through alpha 5 is fixed, that means that's equivalent to saying it fixes K. Here these are F automorphisms of K prime that fix beta 1 through beta p. Okay, so if sigma fixes, sigma is in H intersection H prime implies sigma is an F automorphism of K prime that fixes all the alpha 1s, alpha i's and all the beta j's. But K prime is generated by those. So sigma is identity, right? So it fixes F, it fixes alpha 1 through alpha 5 and it fixes beta 1 through beta 5. So it better be identity. So H intersection H prime is identity. Okay, so that's good. So now consider the canonical map. So I'm going to call this phi from N to N mod H, which we know is isomorphic to G prime. Kernel of this map is H. So restrict to phi, restrict to H prime, because H prime is in N, right? So H prime to N mod H. So kernel of the restriction is the kernel of the original map intersected with H prime, right? Obviously when you restrict, it is all the things that go to identity that are in H prime, but this is H intersection H prime. So this means this is identity by the claim there. So this implies phi restricted to H prime is a function from H prime to G prime which is isomorphic to Z mod PZ is injective, right? Remember G prime is Z mod PZ. So N mod H is isomorphic to G prime. So H prime to that there is an injective homomorphism. Hence we have two cases. H prime is either, so H prime is isomorphic to a subgroup of Z mod PZ. This implies H prime is either, Z mod PZ is a group of order P which is a prime number. So it has only two subgroups. Either H is trivial or H is equal to, or H prime is trivial or H prime is isomorphic to Z mod PZ. Okay, so there are two cases. So this is case 1, this is case 2. So H prime is either trivial, so H prime sits inside Z mod PZ. So that means H prime is either trivial or Z mod PZ. So case 1, H prime is trivial. If H prime is trivial, then let's look at this map. N to N mod H prime, which of course is G, which of course is by hypothesis A5. So now what can you say about this map? So this map is onto, right, always. This is the canonical map from a group to that group mod a normal subgroup. Right, so this is onto, but it is also 1 1. Why is this? This is because kernel is H prime, which is identity. Kernel of this canonical map is H prime, which is identity. That is the case that we are taking. So we have an onto map, and which is an injective map. So N is isomorphic to the alternating group A5. So N is simple. So here we have to use the fact that, which we haven't proved and I hope to prove this later, that A5 is simple. But I claim that this is a problem because N does have a simple group, normal subgroup H, right? H is a normal subgroup A of N such that this H. So maybe I should just draw the picture again here. So you have K prime, K, F prime, F, and this is N, this is H, this is H prime, this is G, which is A5, and this is G prime, which is Z mod PZ. This is really an isomorphism. So N does have a subgroup, normal subgroup such that, so H is not trivial obviously, because N has 60 elements, right? So cardinality of N is 60 and cardinality of is P, right? So this implies cardinality of H is 60 by P, but 60 by P is less than 60 and bigger than 1. So cardinality of H is not 1 and not 60. So H is a proper non-trivial normal subgroup of N, which is A5. But this violates the fact that A5 is simple. Simple means it has no non-trivial proper normal subgroups, but N does have a non-trivial proper normal subgroup. So this case cannot occur. So H prime can't be 1. Correct? So I hope this is clear. So if H prime is trivial, then you violated the simplicity of A5. So case 2 is H prime is Z mod PZ. That means this is Z mod PZ. So in this case, we conclude that H must be Z mod PZ. So now let's just do some simple group theory. So we know that order of N is order of, so because N mod H prime is isomorphic to G and N mod H is isomorphic to G prime. So it at the same time this is order of H times order of G prime, right? This is what we have. And now this H prime by hypothesis is, of course, G is 60 because G is A5 and H prime by this assumption is P. So this is 60 times P. H is whatever it is. And what is G prime? Sorry, this is H prime, yeah, and G prime is Z mod PZ. So this is P. Okay, so Z prime is Z mod PZ. So this is P and this is H. So these are equal. So this implies order of H is 60. So you have a subgroup of N of order 60. And now we are done almost. So now consider the canonical map N going to N mod H prime, which is isomorphic to G. Right? So N mod H prime is isomorphic to G. So we have N going to G. I'll omit that. This is surjective, right? Surjective. Let me write as onto. And now we have a subgroup H here. And this goes to this. Okay. What is a, so this is psi. And this is psi restricted to H. What is the kernel of psi? So this is psi. I don't need that it's onto, but psi. So what is the kernel of psi restricted to H? This is kernel of psi restricted to H. This is H prime intersected with H. This is 1. So this is 1, 1. So psi restricted to H, just like in the previous case. There we looked at N to N mod H and restricted to H prime and concluded that it is injective. So it is isomorphic to Z image, Z mod PZ. Here it is image is G. So H is isomorphic to a subgroup G. But what are the orders of these groups? Order of H is 60 by just what we concluded here, which is also of course order of G because G is A5. So you have an injective map from G to H to G and both have order 60. So this implies H is isomorphic to G as required. So this is the claim that we made, which is of course the claim that I wrote here. So for any Galois extension which is a prime whose degree is a prime number, if the K prime is the splitting field, then the Galois group is A5. Now, so this you may have forgotten the original situation. What is it that we have? We want to prove that F is not solvable. We assume to the contrary that F is solvable and we have this tower. Okay. So let us now copy this tower. So if alpha in K is a root of F that is solvable, right? So for a contradiction we assumed this. So we have a tower like this. So I'm going to write it like this. So you have F, F1, F2, F3, Fr minus 1, Fr. Okay. So this is the tower we have. And this is prime, Galois, and the degree is prime. Galois, degree is prime. Galois, degree is prime. This is Galois, degree is prime. This is Galois and degree is prime. Okay. This is the equivalence of the four characterizations of radical extensions. If alpha is radical, we can construct such a thing. Now we have K, which is the splitting field. So this is the splitting field of F over capital F. Okay, and this by hypothesis degree Galois group is A5. Right. Now by the claim we have K1. And what is this? This is the splitting field of F over F1. Okay. So this is this picture here. I am just applying with F prime equal to F1 and K as it is, F as it is, and I have K prime which will be now called K1. So this is a splitting field of the same polynomial over this larger field. But this is A5. This statement is from by the claim. This is by the claim. Now let's see where we are. Now you forget the original situation. K over F you forget. So you forget this part. F1 is a field. Small f is a polynomial of that field. Its splitting field has Galois group A5 and we took a Galois extension with prime degree. Of course that is important here. So this is a Galois extension with prime degree. So we take the splitting field. So this is the splitting field of F over F1 or F2 now. Over F2 now. And by the same claim. That is A5. So you can keep going like this. So you have K3 here, and if this was F3, that would be K3, and you have Kr minus 1 here, that will be A5 also, and this will be A5 also. At each stage we have a Galois extension with prime degree, Galois extension with prime degree. So by repeatedly applying the claim, we get A5 and finally we get Kr, right. So just to make it abundantly clear, Kr is the splitting field of F over Fr, right. and this is A5 because of the claim. So the claim is applied to this square, because f is a polynomial over capital Fr minus 1 whose Galois group is A5. We took a Galois extension of prime degree and took the splitting field of f over that extension, and what you get is a degree A5 extension. But this is now a problem. Why is this a problem? This is a problem because, so maybe I'll try to write it here. Because f splits in Fr, right? Because it has a root. Right? The whole tower was constructed so that the last field in the tower contains a root. So f splits in that field. So f has a root in that field. So sorry, it doesn't split completely. So all I will say is that f is not irreducible in Frx. So f is not irreducible in Frx because it has a root. So the Galois group of f, so that means we have f equals x minus alpha times f prime, where f prime is in Frx and degree f prime is 4. So the Galois, the splitting field of f over capital Fr minus Fr, which is of course Kr, is the splitting field of, so maybe I'll just rewrite here. So Kr, which is the splitting field of f over Fr, is actually the splitting field of f prime over Fr. Because f factors as f times f prime x minus alpha times f prime, alpha is already in Fr. So in order to attach all the roots of small f, you just need to attach roots of f prime. But this means Galois Kr over Fr is a subgroup of S4, because it is the splitting field of a degree 4 polynomial, so it must be a subgroup of S4. This in particular means its order is less than or equal to 24, but we have already established that Galois Kr over Fr is A5, so has order 60. So this is the contradiction we need. We are looking for. Okay, so because f already has a root, you don't need a degree 60 extension to get all the other roots. In fact, you need at most a degree 24 extension. So if this is A5, this is A5, this is A5, this is A5, this will be A5. So there is no tower like this. The conclusion is there is no tower like this, and hence f is not solvable over capital F. If there is a tower like this, f1, f2, f3, fr minus 1, fr, we obtain a contradiction. So f is not solvable. So this completes the proof that any degree 5 polynomial whose Galois group is S5 or A5 is solvable. So we sort of take care of this, right? So we proved that, we proved star here in a separate way. And next we will address the question of whether in fact there do exist such polynomials or not. And I said there are lots of such polynomials. We will do that and then we will start doing some problems. Okay. So this completes the proof that there are If, so I should not say there are quintics that are not solvable, but it completes the proof that if there is a quintic polynomial whose Galois group is S5 or A5, it cannot be solvable over that base field. Okay, so let me stop this here. In the next class, we will see such examples of quintics whose Galois group is S5 or A5, and thereby producing quintics that are not solvable, and then we will go to some problem sessions. Thank you.